Welcome everybody. We are back for the embedded Rust class, and I'm sorry for last week we couldn't make it due to some technical issues, and we apologize. And I guess this will be the last of our series before we have our question and answer series where we get to ask Professor Brad a lot of things, and then we get to figure out things. So, for emphasis sake, please do make sure to check our Zulip channel, the Ross Edu Zulip channel for Ross Africa. Make sure to check up the GitHub. Make sure to check up the Ross Discovery book because these are the things we have been working with so far. And for today, I will give Professor Brad the grants to give us a masterpiece again. Thank you very much.
Oh, don't be silly. Yeah, I think we may actually just wrap up today, depending on how things go. We have about a half day, day's worth of material left to cover because we're getting near the end, and I'm really, really excited about what we've gotten to do. I hope all of you who remain are as well. It's been interesting, and I've learned some stuff about what we still need to do with the book and some other things. So it's been really great for me also. Let's see. Let's start with picking up. We were left off right at the end a week ago with interrupts. I sort of waved my hands real fast at the last bit of that chapter. And so I'd like to start by doing that again, picking that up again and looking at it in a tiny bit more detail, just so we can see what's going on, because I think there's some interesting ideas and some interesting code there. And then we'll jump forward to the last chapter of the embedded book. So if you'll remember, last time we were talking about interrupts, which are the processor stopping whatever execution is going on and jumping to an interrupt handler to process stuff related to something that changed in the hardware or the software. And in particular, we played a lot with button interrupts and debouncing and that sort of thing. But at the end, we did a little audio demo. And I want to look at that audio demo a little bit more closely to see what's going on here. And let me pull real fast the other thing, the book, and we can take a look a little bit at what was going on there as well. So let me switch to a screen here. So this is the code for our siren. This thing's going to make a siren, and a siren is just a tone that rises and falls in frequency. The pitch goes lower and higher as, in an oscillating way over time. And so there's a lot of ways you can do that, and we could actually even do it with the main program. We don't need interrupts. The thing is, you'd like something to be able to happen while the siren is running. And so what we'd like to do is toggle the speaker when it's time, but not under the control of the main program, really. We don't want the main program to have to do anything. We're just going to start our siren, and then the main program is going to keep running. So let's skip down to that first. Let's talk about the siren itself. Here's the siren object. This is the first time, too, I think, that we've sort of done a bunch of implementation for a struct. So this is a Rust struct, a structure, and it contains all the information the siren interrupt handler needs to do its job. It contains the timer used by the siren. That's just a timer peripheral from the processor. It contains the speaker pin, which is just a GPIO pin from the processor. It says whether the pin is currently set high or low, because you want to just remember that. And it sets how long it's been in microseconds, millionths of a second, since the thing started. Can you see this okay, by the way? Is the entire screen visible? Because it's not clear to me whether it is from my doofy setup here. It looks like it might not be. Somebody tell me what you're seeing here. Is it cut off? Is that struct cut off at the bottom?
It's very visible. It's very visible. There's no issues.
So the whole window is visible. The whole streaming window is visible. Okay.
I think the struct part is a bit
I
cut
think
off.
cut off. I think it's cut off at the bottom. I'm going to try to fix that real fast. Apparently something has changed since my last setup, so we'll just fix that. That's easy enough to do, I think. No, not gonna. There we go. That's probably better. We will grab it one more time. Sorry about this. I didn't realize we had an issue, so I didn't even think about it being a problem. So let's put this like this and this like this, and there we are. Now you should be able to see the whole thing. So yeah, that's the timer struct. And what we're going to do is we're going to implement methods for that. So we're going to be able to make a new timer struct. We're going to be able to start the timer running, the siren running, by just setting up that timer struct and turning on the interrupt for the timer. So what we're going to do is have the timer go off when it's time to change the speaker output. I guess to understand all this, maybe the easiest way is to draw some stuff here. I'm not sure I've said everything that needs to be said. Let's see. Let's do this. Grab a pen here and switch to the .cam view. Yeah, so the sound is air pressure, and the air pressure comes out of a speaker, and the speaker pushes in and out. It pushes out when the thing's high and in when it sucks back in when it's low. I feel like we have talked about this. And so what we want to produce is on the speaker output is a wave, like a square wave like this. This is time going this way, and this is 1 or 0 that oscillates like that so that it will make a tone, right? And we want this to vary around, I don't know, 440 hertz or something like that, 440 cycles per second. But the point is that as the siren gets higher pitched, these will get closer together. And as the siren gets lower pitched, these should be farther apart. And so we're really trying to produce a very specific pattern of in and out of the speaker that will produce this siren tone. And that's what all this machinery is for making that happen. And to do that, we're going to use the timer peripheral on the NRF. And the timer peripheral is literally a thing that can, among other things, set off an interrupt after a certain amount of time. So that's why we're doing this enable interrupt line, is we want to, when it's time to flip the pin again, we want to take an interrupt, and that interrupt will do that. And then we set the starting frequency of the timer. We set the time to be 1,000,000, because that's just the base units of this, divided by our base frequency. So every time that timer goes off, we'll take an interrupt to deal with stuff. And to stop the siren, well, we just disable the interrupt so it quits changing the speaker. This is the thing that actually handles making the siren. This will be called from the interrupt handler, and it figures out which way the speaker pin is, flips it to be the other way, figures out how long it should be until we flip the pin again, which is kind of a fancy calculation. I won't go through the details here. It took me a long time to get right. And then having figured that out, we go ahead and set the timer again to start with the new next time period after this. This instruction is critical. This is the thing that resets the timer's event so that we don't just immediately interrupt again. That's important. So having done all those things, then this is our interrupt handler. It just calls the step function. Notice that it has to lock this structure because something may change it. In particular, you may stop or whatever. And so we do that the normal way that we've been doing it all along. So that's the code. And then the main program just makes a new siren, starts the siren, and then it counts down from 10 down to 1, delaying each time. This is the kind of fun Rust right here. We're going to count from 1 up to and including 10, but we'll do it backwards. And we can do that with .rev, and this is by far the easiest way to do this. And so we just reverse the counting, and that's easy to read and clear. Hello, Rafa. Good to see you. And Mr. Rafa. And and then we put pret launch. So the idea here, the fun idea is that we've got a rocket on the pad, and that siren is the about to launch siren, and we're counting down until we launch the rocket. I used to be the faculty advisor for the Portland State Aerospace Society, and we have turned on a siren and launched a rocket a lot of times. So this one has some resonance with me. So I'm going to put the micro bit where you can hear it because it doesn't do anything interesting. Let me dig out the board again. Where is it? Right here. And let's go ahead and load it up and run it and watch it work. Or listen to it work anyway. Oh, sorry, I should have the screen on probably. Oh, I do. Okay. Oh, and it takes a while to build this stuff sometimes. I don't know what's going on. So that's the siren demo in more detail. The important thing is that this stuff, the countdown stuff, is happening at the same time that the siren's running, but the siren's sort of running in the background. You don't have to pay attention to it. You just turn it on and let it run. So that's interrupts in a little more detail. Let's go on to the last topic in the book, which is to put this all together by making a little game here. The goal here, let me grab the book again, is to build a snake game. And I don't know how many people have played Snake. The idea of Snake is that you run a little guy around a snake around a 2D grid picking up food, and every time it eats food the snake gets longer. And let's just start by demoing that, and then we can work backwards from there, I think, to look at the code a little bit. The reason that we end the book with this project is because it sort of wraps up a lot of the things that we did during the course of learning embedded into a single sort of program that is fun to think about. Sorry, my setup here has gotten a little screwed up by all the changes in the camera and board and stuff. Let me take a second, set this up so you can see it. So do it like this again. That should be visible enough, I think. Let's flip it over here. We'll go to this view, I guess. Yeah, that's interesting. Not sure what I've done here. All right. It's fine. That's fine. All right. So let's just go ahead and build and run this thing. Oops, except this is messed up again. Sorry about that. Let's fix it. Oop. Yeah, there I am. I knew I was there somewhere. I'm just underneath, and that's fine. There we go. Now we got everything set up the way it's supposed to be. Sorry, I made some changes recently to my setup, and apparently they got messed up. So let's actually just run this straight out, and we'll play some Snake, and then we'll figure out how this game is actually built. So the LED turns on, and you see the little snake running around. It actually wraps around when it gets to the other side of the screen. And that glowing blob there is the food. And I can turn left with the A button and turn right with the B button to change which direction I'm moving. So if I push left, now the snake's going like this. And if I turn right again, now the snake's going like this. And when I'm ready for some food, I grab some food by, oops, nope, missed it. Let me try one more time. There we go. By turning right at exactly the right time. And now the snake should be one longer. I guess it's one longer. Oh yeah, it is, but it's really dim, so it's hard to see. Sorry, let me change the lighting here. One moment, please. That should make it easier to see that now my snake is not just 2 long, my snake is 3 long, and he's driving around. And if I ever run the snake into himself, then I lose. So I can't do that. Now I'm going to the right. And now I got the snake, and now my snake is 4 long. And I have to start being really careful I don't run into myself. And now if I screw up, I'm about to die here. I'm going to eventually run into myself. I ran into myself and I lost. And now the game resets and starts over. And that's the snake game. It's an old game that used to be played on people's personal computers. You normally see it as a computer game. But because we have this 5x5 LED matrix, it's kind of a fun game to implement for our setup as well. So that's what we've done. Yeah. Kind of a fun exercise. So let's get everything out of the way here a little bit. Go back to this and see what's actually going on. Right. So how did we do this? Well, we did it doing a lot of the stuff we've been talking about for the entire class. There's nothing very new here, just a lot of the same things we've had all along. So let's look at this a little bit. and see what we can figure out. Let's start with the cargo.toml, because that's always a good place to start. Why is this dependency here? I don't think we need it. And this, interesting. We got more dependencies than I remembered. In particular, I don't think we should need tiny LED matrix or heap list. But anyway, we've got all the normal crates, the microbit crate, the Cortex-M runtime crate, the stuff for printing and printing when you panic. And we also have the embedded HAL crate because we want to use it directly sometimes. Or traits because we want to use them directly for the buttons. So that's what we got, plus the Cortex-M crate, as always. So nothing very exciting there. I'm super curious. That's wrong. Okay. All right, never mind. I'll deal with this later. All right, let's look at our main program. First of all, let's look at our source directory. Look what's in here. There's a whole bunch of files. This is the first time, I think, in this course that we get to talk about Rust's crate and module system. Rust module system. So Rust has modules. You can break a source file up into modular pieces. And here we have a lot of code, so we've broken it up into a lot of pieces. We also did it to illustrate Rust's modularity. An important thing to notice is that these modules aren't compiled separately. When you go to compile a Rust program, it treats all the modules as one big Rust program and doesn't compile just pieces of it. It compiles the whole thing. That whole program compilation is great in some ways, but it certainly increases compile time in normal situations. So let's start with the main program and see how this all works. It's got these mods. I don't know why this one's pub and the others aren't, but it's got these mods. Oh, I know why, because other things re-import it. So yeah, controls, display, and game are modules. And their source files are named the same thing as the modules themselves, except that, so if I look at game.rs, that's just where the game module lives, which contains a bunch of game state. And you can see this is already a pretty big piece of code. So you can see why we broke it up into modules to make it clearer and easier to understand. The controls and the display are also their own modules, but these are a little different. These are Rust modules that themselves have submodules. So if I look at controls.rs, what I'll find is that it has its own modules for initialization and interrupt handling. And let's look at, and the same thing with display. Has its own interrupt and show modules. And so we got a lot of code in here that depends on the module system in interesting ways. Let's go back to our main program. And you can see here that we get the get, turn, and init buttons function out of the controls module, the clear display, display image, and init display function out of the display module. And then from the game module, we'll use the game struct and the game status struct or enum, I think, to do our job. One thing this program is severely lacking, and I would love a pull request that corrects it, or I'll eventually do it myself, is comments. This code is not very well commented. It needs to be better commented. But this is the usual stuff we've been doing every week for a long time now. None of this should surprise you very much. The only thing here is we remember that a long time ago we messed around with the grayscale image and bit image stuff of the non-blocking display. Here we're going to make big use of the non-blocking display. So this is the main program, is just this chunk of code. It fits on one screen more or less. we're initializing printing because we want to print something. We do the usual things. We're going to set up a timer, a random number generator. Now that's interesting. This board actually has a hardware random number generator. And when we place the food, we want to place the food at a random spot on the board. And this random number generator is how we're going to do that. There are other ways we could have done random numbers, but this is by far the easiest. And so we'll just use the hardware random number generator. Modern CPUs are crazy. And then we make a new game struct that needs the RNG to function. And now we're almost done. We initialize the buttons so that it will it can take button interrupts. We initialize the display so that it can take display interrupts. And here we go. We have two loops. The outer loop is just run the game and then reset the game to start again. The inner loop is the actual gameplay loop, and that will fit on one screen. In that loop, we figure out what we want the display to look like. And it turns out the easiest way to do that is just to take the game's map of what the display location should look like and turn it into an image and display that message. And then we're using the non-blocking display only because we want grayscale. We actually now just block. We delay for whatever the step time is, right? This step length in milliseconds is how long the game is going to wait before it moves the snake. And that number obviously can be tuned to be faster or slower. When you make it faster, the game gets harder. When you make it slower, the game gets easier. I chose it to be pretty easy because I want, the point isn't the game, it's the code. And then we check the game status and see if the game's still playing. If it is, then we just step the game after getting the button state to find out whether we should turn the snake. Otherwise, when we're done, we clear the display and show an image and break out of the loop so that we can start the next game, reset the game, and start over. This wouldn't have to be two loops. This could definitely just be one loop. But I think it's clearer this way, and so we left it that way. I didn't write this code, by the way. Originally, it was written by Alan, somebody. It's in the cargo.toml. But I've edited it quite a bit over the years. All right. So the interesting things that are still here are the game module. And the game module just deals with this game struct that we defined that says, are we playing or not? It holds the random number generator for when we need a random number. It holds a snake struct for when we need the snake, and that's in a separate module. We have modules everywhere here. It holds food coordinates from the chords module for where the food is right now. It has the speed, which says how fast we're going to step the display, and it has a score, which says how long our snake is, basically. So when we make a new one, we just set all this up. We go get the PRNG. We get a pseudo random number generator from seeded by the hardware random number generator, which is probably unnecessary, but it's what we chose to do. We make ourselves a snake, and then we get some random coordinates for the food. And then we make our game struct with all that stuff in it. This is just normal Rust struct initialization at the end here. And now, when we want to start a new game, we can reset this all to do stuff again. Here's how we place the food on the grid randomly is we call the um, random number generator to find a place to put the food, and then we just say, well, that's where the food is. That's the whole story. Notice that the snake wrapped around the screen, right? That was a choice. It makes the game easier to play. So we have to, if we're about to wrap around the screen, we need to put the coordinates back to where they go. That's what this does. Here's the idea here is to figure out where the snake's going to find out if it collided with itself. So here's where we find out what happens from the next move. We don't actually change anything yet. We just find out what happens from the next move. We look to see where the snake is, and if we've collided, is that code even right? I guess it is. If we've collided, then we say, well, we're going to collide, and otherwise the outcome is let's make the move. I don't feel like that collision detection is correct. It only is checking for collisions with the tail of the snake. That doesn't seem right. But hey, today I learned. And then we see if the snake has hit the food. If it does, we indicate that. And otherwise, we just move. Yeah, the collision detection's wrong here, I think. I should be able to prove that. Anyway, and then here's where we say, well, let's deal with the next step. And so altogether, the step here is turn the snake if we need to turn it, find out what's going to happen, and then deal with it. And that's the whole story here. The step-length millisecond uses the speed coordinate and does a fancy calculation. Notice that the snake speeds up as it gets longer, and that's a way to make it harder. And that's an interesting plan that we have here. And this is how we go to a brightness matrix for the LED from the actual state of the snake. So this is just going to basically be the thing that decides what the LEDs should be doing right now. And it does that by looking at the little matrix of where the snake is and where the food is. It does the coordinates where the food are, and it looks at all that and says, well, here's what the display should look like. And it basically just returns a two-dimensional array. Look what it returns. It returns a two-dimensional array of U8, which is nice because it can just return that by value. It's perfectly fine. And then that thing it printed, it showed at the end when we lost is the score. And so it's going to give us 1 point for, one LED turned on for each length of this, up to the length of the snake. So yeah, that's the snake game. The other modules are interesting in their own right. Let's look at the display module, which does a whole bunch of things to make sure that the display can be driven by an interrupt. And down here in the interrupt module is our interrupt that when the timer goes says, oh yeah, you should probably deal with the display. This is how you use the non-blocking display. I think we did it before, but we certainly are doing it now. And it requires us to deal with interrupts. And that's a small piece of code, but pretty useful. The other thing in here is show.rs, which um, can either turn off all the LEDs, or it can take an image that you're supposed to do. And the image is from render.rs or somewhere from render, wherever that is. So yeah, that's display side. The other side is input.rs. I don't remember anymore. Controls.rs. Controls.rs handles the buttons. And again, the buttons are likely to be driven by an interrupt. Yep, there's a button interrupt as well. And that one's just a GPIO interrupt. It says whenever a button's pushed, update the button state. And it uses this turn variable, global turn variable here, to say what state we're in, whether we're turning left right now, turning right now, or just going straight. And again, if I look at the interrupt handler, we find that the interrupt handler is a little fancier here because we have to figure out what's going on with 2 GPIO pins, but it's not a big deal. And this is called every time you push a button and updates the state to see what's going on. This is not really debounced right now, but it doesn't matter very much because the buttons are only sampled the button state is only sampled every time the snake moves, and so that effectively debounces it. So that's the snake game. There's a lot of code here. How much code is there here? 450 lines of Rust, which is, 522 lines counting comments and stuff. Comments and blank lines. That's a lot of code. It's much bigger than anything we've done so far. And the reason that we end with this is partly just for you to be able to see that you can write big things with Rust too. You can write things much, much bigger than this without too much problem. And Rust scales really well as you get to larger problems. A lot of people do embedded development with Arduino, which is a C++ IDE. And Arduino is great-ish if you've got 20-line programs to write, like we did a lot of the time in this class. But when you get to these big programs, Arduino becomes pretty unmanageable. C and C++ have kind of weak module systems, and so they don't really have module systems, and so it becomes really hard to do this kind of bigger stuff in C and get it all to work well. But in Rust, not such a problem. Let's run this one more time. I'll go turn the lights off again, and we'll reset it. Well, I guess it's running now. And so now that you've seen all the machinery, maybe you appreciate a little bit better what's going on with our game. Let's see. We got a too long snake. I guess we start with a too long snake. And because that's right. So let's do this. Let's try to break it. Let's go. I think you can see the whole display now. Let's go left. Oops, that is not left. Right. Oops, now I've done the thing. I can't drive, sorry. You're all better snake players than me, who knew? Now our snake should be 3 long. It is. The food's down here. Now our snake's 4 long. I'm going to try to intersect the middle of the snake and see if it works right. So let me try that. Oops, I went the wrong way though. Let me try that again. I need to go 3 lefts real fast. 1, 2, 3. Yeah, see, that crashed with itself and it didn't intersect because the intersect test is buggy. It's funny, yeah, exactly. We tested it, it fails. So nobody's ever reported that bug. I've been working with the Rust Embedded book for a couple of years. We've never had a bug report that says collision detection is broken for the snake. That's interesting. That's super interesting. And what that tells you is a couple things. So let's finish on that, then we'll take a little break here. One of the things it tells you is that it's hard. V&V, validation and verification, is hard, and it's hard in any setup, but it's especially hard in embedded. Normally what we would have done to prevent this problem is we would have written a ton of unit tests. We would have written a ton of tests that run and try to figure out whether this stuff is working. The problem is that you can't really run tests using Rust testing framework because the test macros and stuff want to run on the machine that's compiling, right? They don't want to run on the microbit, and yet you need them to run on the microbit because that's the only place your code works. So it's very hard to write tests for this code. And what that leaves you with is inspecting the code really carefully, which is really super important. And it turns out that we inspected the code pretty carefully and found a bug. And that's how you find bugs usually in embedded programs. Either something fails at runtime in an obvious way, or you are reading the code and find a bug. And that really emphasizes how important it is to just read your code. And so maybe after the break, we'll fix this bug and then do a little question and answer. If anybody has questions that they want answered at this point, I'm happy to do that. And then maybe we'll call this a course. I feel like we've done enough now that anybody who's made it this far, and thank you for making it this far, is ready to do embedded programming on their own. So let's take a little short break and then we'll come back and do those two things. Sounds good? Cool. See you in 5 minutes. All right. Pretty close here to being back. Let's see. Weird. All right. Has that been 5 minutes yet? I lost track, but probably ready to start again if everybody else is. What do you think? Cool. All right. So we have, I think, a couple bugs to fix. I've been thinking about this, and I think what we're going to do is do a little bit of bug fixing at this point. First of all, what branch am I on? Main. Good. All right. So here's some changes that have been made. Always start that with your get stuff before you do anything. Let's make a new branch and fix that the snake is too dim to see. I think that's really the first thing we should fix, and it'll be really, really trivial. So we'll start with that. Somewhere in here should be the code, probably in display/show.rs should be the code. Nope. Where is that code? Probably in snake. Interesting. Game /snake.rs. Let's see if that's where it is. Snake, turn right, turn left. Nope, that's just the snake stuff. How about, nope. Is it here somewhere? New, reset, place food, wraparound, gen next move. This is the problem with large things with a lot of modules, is you have to find where things are. There we go. Game matrix. That's what I wanted. And it's using things called head brightness, tail brightness, and tail brightness is called, so I think it's the somewhere that we're calling game matrix. Our ripgrep is one of the gems of Rust. You can cargo install ripgrep, and you'll get the RG command, which will search a whole directory of stuff really, really quickly. So it looks like in main, it's just the main program, and that's what's setting these brightnesses. It's actually probably bad game design, but source design, but there we are. So we have this brightness set to 3, and that's pretty clearly not okay. I'm going to set this to 7 and 5, I think. And we're going to see if that looks any better. So let's just do this dumb change of 2 numbers first and see if we can now see the display, which would be really nice. Hey, that looks better, but you still can't quite see it. I guess I'm going to have to make it even brighter. Did it change? It should have changed. I don't know. Let's make it even brighter then. We'll go with 7 and 6. Yeah, it's a little hard to tell the head from the tail now, but it's still doable, and that's a lot easier to read. So I think I'm going to leave that. Increased snake tail brightness. And then let's go ahead from there and fix the thing we actually wanted to fix, which is the collision detection algorithm. And we'll do it in a little bit of a fancy way because this is fun. Where was it we were looking in source slash? Well, let's just look in main and figure out where it must happen. It happens in game somewhere, I'm pretty sure. Game.step. No. Game.step, yeah. Right. It was in get step outcome, and it's right here. Right. Right. So this says if the next move's not. Oh, wait, there shouldn't be a bug here. This is frustrating. So there shouldn't be a bug here. If the snake coordinates contain the next move, and the next move's not the tail, I see. So I was misreading this, and I'm not even sure why I was able to reproduce something that looked like a bug. So let's try this again. See if we can really reproduce the bug here. Because, yeah, what we're actually doing is if the snake's coordinate set contains the next move, then it's a collision unless, if you're moving on to the snake, then that's a collision unless you're moving on to the tail. And the reason it's not a collision, I misread the code before. The reason it's not a collision there is the tail's about to move out of the way when you move. So the last part of the tail is supposed to move out of the way when you move. So that's actually a fix for a different bug. And we're in Rust, so we should be operating on 100 lines. So we can read that comment. Yeah. Okay, well, clearly my testing failed. I clearly was doing it wrong. Let's try this again and see if we can reproduce this non-bug now. Now we'll let this go. Now we got a 3 snake. And then we'll, at the appropriate time, go get that and have a 4 snake. And now I got a 4 snake, which should be enough to reproduce the problem. I should be able to, actually, we should be able to first make sure that a 5 snake works. Let's do that. Oops. We self-collided. And we self-collided with something that wasn't the tail. So my non-bug was actually a non-bug. Interesting. All right. Well, that was easy. I'm not sure why I thought I'd reproduced it successfully before. Probably I was just driving wrong. And this again points out how important it is to test your code and how important it is to inspect it well. All right. Well, we at least made the snake a lot more visible, which I think is actually a huge win. I am very happy with that modification. The other bug doesn't need to be fixed. And so I think we're done with the snake. So that's what I got for you this quarter is this class, I think. I think the last thing is just to do Q&A. And I think we've got plenty of time. We got a half hour for any questions you might have, any issues you'd like to discuss. And then I think we can call this whole thing a wrap. So that was a lot. It was really fast. I know that, a lot of you were following along on your own, and so it wasn't so bad. But please understand that this was a very, very fast whirlwind tour through a complicated topic. And so don't feel bad if you got lost at some point. Just go back and go through it again and figure it out. I will be on the Zulip indefinitely, so you're welcome to bug me there. And yeah, happy to answer questions on the Rust Africa embedded Zulip if you have them. So we have questions or issues or other stuff that people would like to talk about this week. Yeah, there is actually an ESP3 book. That's not really like the embedded book. It's it's not an intro book, but it is a pretty good book on how to get started developing with the ESP. Rust ESP 32C book. Let's see what I can find here. The Rust on ESP book. That's what I was trying to remember. It's at yeah, it's on the Espressif website actually. Docs.espressif.com has a pretty good book. This is pretty beginner friendly, and it definitely helps you figure out how to set up your stuff and get going with the ESP32s, both the ESP32C and the ESP32S. So it shows you what the dev kit they're working with looks like, and tells you what crates you need to use, and what's going on with this stuff. I need to work through this. I haven't yet. I've got an ESP32 board sitting on my desk back there that I've been meaning to fire up and run for a long time now, and haven't made much progress getting around to. But I have a lot of friends who've used ESP32 with Rust just fine and say that it's a pretty good experience. So that's nice. What else? And I don't know how many people we actually even had finish. I'm sure a lot of people fell off somewhere along the way, which is fine. They'll get back to it when they get a chance. But I think we might be done. Oh, there we go. Is there lifetime use in embedded? That is a great question. So, yes, there is. We've dodged it really carefully in the Rust embedded book because we didn't want to confuse people with yet another complicated Rust topic. There's less of it in embedded because most stuff is either on the stack or static. It is a complex topic, but in embedded, most of the stuff is either on the stack, it's either local to your function, or it's static, it's global and will last forever. And in both those cases, lifetimes aren't very hard, right? Taking a reference to something that's global, lasts forever. The games we've played with making global mutable variables using the lock mute crate hide some of this lifetime stuff that you would otherwise have to deal with. But yeah, it'll come up occasionally. One place where it comes up on the microbit is if you look at the channels. Let's see, where am I? Yeah, in the snake game is the one place where it's used. In here, and we carefully hid it from you, really super carefully, by not making the lifetimes be anything. And the way we did that was that we made the whole GPIO be GPIOT, the peripheral be global, and we made the GPIOT, the whole GPIOTE peripheral be global, and then we just use that. And the reason we did that is because lifetimes actually, let's look at NRF 52833 HAL, which is what we're using under here, to GPIO. And if you go look at, no, not GPIO, GPIOTE channel returns a channel with a lifetime, right? And what you'd like to do is store that channel globally, not store the whole GPIOTE globally. But because the channel has a lifetime, to store it statically means that you'd have to store the GPIOTE statically somehow anyway. And so we just cheat and grab the channel again from the GPIOTE. We call the GPIOTE's channel zero method again every time we want to use it. And that's to dodge the lifetimes. And it would be better if we had some better plan. What really needs to happen is that the GPIOTE channel needs to use a cell or something so that it doesn't have a lifetime like this. This is a weird pattern and probably not good Rust, but it's the way the crate is right now, and we should fix that at some point. So that's one place where lifetimes would have come up, but didn't come up because we dodged it that way. And that's a lot of times what you do with lifetimes is just dodge them by not keeping references to things with weird lifetimes. You'll notice we didn't use a lot of references in this course, or at least not use them in interesting ways. That's often really good Rust, is just to say, well, Rust references are what they are. Let's not. And I do that even in, fancy code I write. I will avoid a reference until I desperately need a reference for something, and then you'll have to deal with lifetimes potentially. Does that make sense? Yeah, looks like it does. Cool. So you wanted to say something, Mordecai? When you're working in non-embedded Rust, yeah, you end up doing cloning sometimes. Once you get used to lifetimes and ownership, you can usually get away without cloning your strings, but there are worse things to do than cloning your strings by a lot. Whatever makes your program work. If it's a serious efficiency problem, if you're cloning giant strings or cloning strings really fast, then you figure out how to use lifetimes to avoid that. Otherwise, who cares? Life's too short to worry about efficiency first. Rust is kind of a language where you get plenty of efficiency, and so you can throw some of it away in favor of simpler, easier to understand, easier to debug code, and that's fine. It's going to be faster than JavaScript. Anything else? Cool. Well, I think we've done it. I think we've pushed through a lot of really complicated material, and hopefully the people who've kept up have benefited from going through it like this instead of just on their own. I would encourage you to go back to it on your own and review what we've done and take a look at the couple chapters we skipped for time. Oh, it was fun. It was really a lot of fun. And take a look at the couple chapters we skipped for time, which was just more stuff with the accelerometer mostly, accelerometer magnetometer mostly. I didn't think that was key stuff, but they are fun chapters. Building the punchometer is always a fun project. And once you're done, build things. Go out and try stuff on your own that isn't in the book, and grab whatever microcontroller you've got lying around and figure out how to bring it up with Rust and make it do things. That's what we're here for. The other topics we didn't cover very much is we didn't really talk about pulse width modulation, which is an important topic. We didn't talk about the analog to digital converter and the microphone on the microbit. Those are interesting topics. Zulip is the best, either the Rust Edu Zulip or the Rust Zulip. I'm happy to talk to you on kind of any reasonable social media platform, but those are the ones I use the most. You can ping me on either of those, and I'm happy to figure out, how to connect on whatever your favorite is within reason. So yeah. We didn't talk about PWM much at all. We didn't talk about the ADC and the microphone at all. We didn't talk about hooking external hardware onto the microbit. When I teach you the 10-week version of this class, I have the students actually get some hardware that's outside and hook it up to those external pins on the microbit to do stuff. I didn't choose to do that this time because it requires, I don't know, $30 US of stuff to get to the point where you can do that. And so I didn't think it would probably be a great fit for what this is. But if you want help hooking hardware up to the microbit or any other board, I'm happy to talk with you about it. That I2C interface we talked about way back can be used to hook up a lot of things. There's also the SPI, the serial peripheral interface, which is very similar and is supported fine by the microbit and can be used to hook up a lot of things. Plus there's GPIO pins. You can use the GPIO pins to turn stuff on and off. So yeah, external hardware is fun. And that's really the only pieces we left out. I'd like to add an external hardware chapter to the microbit book sometime, but I haven't yet. All right. Well, thank you, everybody. I think we're going to go ahead and call it. But like I say, I'm happy to talk to you anytime.
Okay. All right, everyone. I think at this point we've done very well. And this is the end of our Rust Embedded class. The class ends, but learning never ends. The Zulip channel is still there. You can always hook up with the community in the Zulip channel. Let's see the crazy things you are working on, and let's see the challenges. Let's help you go through it. And then one other thing, the playlist from the beginning of the class till now is there, and it's well organized on YouTube. In case you miss anything, you want to go check it out, you can always go to Ross Africa YouTube channel to check it out. The GitHub account that was created for this course is there. You can always go and check out for external resources. If there are other resources you feel is needed to be added, you can always send a PR. I mean, we are open to accept more PR and everything. Once again, thank you. And for now, we're saying thank you very much, Professor Brad. Thank you for coming to Africa. And even though you are in Africa remotely, and we hope to have you physically in Africa one day. Thank you. And bye-bye to everyone. God bless you.
Thank you all. It's been a lot of fun. And yes, I hope to visit you in person sometime. Take care.